Get your introduction to mechanical engineering on today's episode of the K-12 Engineering Education Podcast. There was a previous episode called Engineering 101 where we gave an introduction to engineering in general. Well, we are back with special guest Sadhan Sathyaseelan to get an introduction to mechanical engineering. Sadhan is a mechanical engineering PhD student at the University of Texas at Austin, and he's going to help us learn a little bit today. So we're learning about mechanical engineering.
Yes. So we're going to go through what mechanical engineering is.
That's really huge though, right?
That is a big topic.
So maybe we're going to start at like the top of the hierarchy.
Yeah.
So in college, if you were to go to college for a mechanical engineering degree, there's like an orientation sometimes. I know that I had one, and they give you that overview. They have like a faculty member or a counselor or whatever and says, hey, these are all the things that you could follow. It's like a board game.
Yes.
Like the game of life. Like it tells you that path that you got to follow in order to get your degree.
It's literally a game of life.
Yeah. So what's on this board game called mechanical engineering?
Okay. So there's a lot here. I think we should first break down what mechanical engineering is in terms of what are the different topics that's in there. I think each of these topics might require its own episode. But for now, I think it'll be ideal if we approach mechanical engineering as how it's taught in a university, how it's approached at a university.
Okay.
And then we can branch off what are the actual conceptual ideas and what are the things that they learn as a prerequisites and what are the things that they learn just as skills. That's not exactly mechanical engineering. Would that be a good way to approach it?
I think that's real hardcore.
Why is it hardcore?
No, that's good. Well, it's like, dang, we're putting people through college here, but in a fun way. No, that's good. Like once you used the word prerequisite, I was like,
oh my God,
I'm in undergrad.
Yes.
So the prerequisite to listening to this podcast is that you have to, I guess, understand English.
That's it.
And understand things that you see with your eyeballs and listen with your ears
and
taste.
Taste? No, maybe touch with your
touch. Touch for sure.
Yes, temperature. If you take a shower, that's fluid mechanics.
Oh, fluid. Yeah. If you take a shower, let's hope. There's a biological system called the vestibular system.
What is that?
It's inside your head. Yeah. Behind your ears, there's this little tiny squiggle-looking thing, a bony structure filled with liquid, and it detects when you're upside down and moving all around.
Oh, the balance.
It's another sense that you'll be using. Okay. So if you're like a dancer or if you play sports, maybe you'll be able to relate to some of the stuff we talk about. Maybe.
Well, hopefully we'll be able to relate it to most people, right? Okay.
And math, and then we'll talk. I'm going to keep
We'll
pushing.
also talk about what math you need to learn.
Possibly, yeah.
If you want to take it as a profession. But if you're just interested in, just what's in there, I think we can just quickly browse through the math part.
Yeah.
Okay, essentially, what is the split?
The split? What do you mean?
Yes, in the hierarchy of...
like the categories of things that you
have to learn.
In mechanical engineering? Well, to me, the word mechanical, it sounds like mechanic.
Mechanic, yes.
Which is like... I go to the guy who helps me fix my car. They use tools. They fix a machine.
Yeah.
They deal with things that move.
So mechanics is definitely a big branch. What does it deal with? Yeah.
So isn't mechanics the study or the field of moving things?
And also stationary.
And stationary. So in what ways? Why stationary? I have to be reminded of this myself. I'm not like, I'm like, I'm being very Socratic. No, I actually don't know Southern. So in what way?
All right. Okay. So this is, I guess an approach would be one big topic that we learn as engineers and as mechanical engineers is mechanics itself. And mechanics is actually a physics concept. It's just learning about forces acting on bodies.
They're on bodies.
Yes,
not like people bodies, but like
it's people bodies too. Objects, tables, chairs. Effect of those things. If you're talking about the liquids, you're talking about the movements of those liquids.
Pressure.
Yeah.
And
you're throwing a ball, that's also like some certain kind of mechanics. So I guess anything that's moving is definitely in terms of mechanics, like
Sure.
what's happening in terms of its mechanism.
But you're right. Maybe not moving. Maybe you've got so many forces on
acting
it,
on one
but
body.
they're in balance.
They're just in balance. So I guess it's statics.
Like me sitting down lazily. There's gravity.
Yeah.
And so it's jogging my memory. I remember learning about forces or dynamics and statics, stuff like that. These are some jargon words, right?
It is.
Yeah.
But conceptually, I guess it's all about forces acting on bodies.
Okay.
And what are the effects of that?
That sounds like forces acting on bodies. Sounds like it could go wrong after a while. But yeah. Well, like,
on forces acting on anything.
On
How about
anything.
that? Yes,
Anything.
yes.
Air.
Yeah.
Cats.
Yeah.
Space. You can't have a force on a vacuum, huh? Because there's nothing there to have a force on.
Anything
right?
that can take a force is what's relevant, right?
Any body that can take a force is gonna.
I guess it's.
I can't take any forces, so
okay, so you're not a.
Don't punch me. Yeah. So okay, we're gonna learn about forces.
Yes.
And motion.
Yeah.
Cool.
Or stationary.
Stationary. Okay.
So I guess it's about material bodies.
Okay.
Solid state
materials.
Yeah,
that's a
solid
keyword
state.
Solid,
liquid, gaseous state doesn't matter.
Fluid.
If it's a material and there are some forces acting on it, even if it's an absolute equilibrium or absolutely balanced forces, I think the entirety of that is talked about in mechanics. So.
Yeah, we got to have a whole episode on that.
Oh yeah, of course.
Newton's laws.
Okay, this is not. There's so many things in mechanics that can branch off. Hopefully, we'll touch upon those things.
So a mechanical engineer has to know this because they're maybe making stuff that apply forces or that take forces or move. Okay,
moving, right?
Yeah.
You just described the automobile.
Hey.
Yeah, so a mechanic in automobile. Everything is moving in there.
Maybe I knew what I was talking about. You also said something about material forces, and I like the word material because I think materials are a big subject in mechanical engineering.
Yes. So I think it's just because we have so many different materials on Earth, and each of them behave differently. In terms of behavior, we mean that if you drop a piece of, say, a metal, and if you drop a piece of glass, when they hit the floor, they behave differently. And this is a very simple example of what it is. But all those different materials have all these different properties that they have. And I think the idea of learning that is so that you know what are the different materials we have,
right,
and how do they behave, and what can they do, so that we can use it the way we want to.
Yeah, like why don't I make windows out of aluminum? Or why don't I make cars out of glass? Like,
exactly. So I guess that's what essentially learning about material is. So what else is there?
I don't know. I guess it's involved with chemistry and biology too. Coming from the biomechanical side, there's this when mechanical engineers have to make stuff that people use or that living things use, you got to choose materials that won't attract bacteria or that won't poison people. So there's that as well. Like we got to think about strength of materials, and whether they shatter or they are easy to bend, but also like, will they cause my arm to fall off, or will they break off into a million pieces in my body? That's bad too. So it's like there's lots of different things.
I just thought of another thing.
Yeah, what?
In terms of material engineering, how big the field is. Just to get a quick look of that. The boom of 3D printing, specifically laser sintering, selective laser sintering, where essentially the technology is just like a printer, like a regular household printer, where it sprays
Ink.
Ink on a specific pattern. It's a very similar thing, except that instead of you have 1,000 pages printing one after another, so you have a 3-dimensional object. That's exactly what's happening. And the entire research, an entire PhD's research was to find the right material that they can use.
Right.
And they found out a nylon compound that works best for that.
You can print layer by layer without it falling apart or melting or whatever it is.
It melts to fume together.
Oh, right. Okay. It melts in just the right way.
Right.
They engineered it.
Yes.
There you go.
There you go. Yeah, that's a good example as well.
All right.
That's awesome. Talking about temperature, heat. That's a big field in mechanical engineering.
People might not think that though. Heat.
Interesting.
They might think, oh, heat is energy. Heat is it has nothing to do with moving parts. So like some people might think that.
It is mechanical engineering.
But you're wrong. Yeah. So sorry. No, but yes, it is mechanical. But why? Why do mechanical engineers care about heat and energy?
Good question.
And that's the end of our episode.
End of my expertise.
My thinking is I guess I'm going to go back to the car example. I mean, cars are run off of energy.
Right.
To get those wheels moving, you're not going to hand crank it, this is not the Flintstones. You have to get the energy from somewhere.
Right.
Meaning, when I want to power my awesome Toyota Corolla, I need to go and get enough gas to power it.
Okay, so that's gas.
Sure.
But this is a study of temperatures or heat and cold.
Well, right. So someone had to create that engine so that it burned my gas in such the right way so that it doesn't burn my entire car, but it also will power the engine inside to start moving or start rotating my tires just the right way.
So by the way, the field of studying those things is called thermodynamics. It's a huge field that comes under mechanical engineering.
And it's another class in college?
It's definitely. I think it's more than one class that you take. A couple of classes that you learn about.
Grad school, undergrad, yeah.
Well, even in undergrad, I think there's a class on thermodynamics and there's thermal systems.
At UT, there's definitely.
Different universities approach it differently. Yeah. Essentially, you're learning about all this, how heat behaves.
Where heat goes. Like if I put a hot cake on my table, how long is it going to stay hot or something?
I wonder if thermodynamics is a field. It is, because again, in my thematic view of this entire podcast is engineering is not a new field. It dates back. Human evolution, engineering go hand in hand, and I wonder if we study thermodynamics in a huge way because we are so. Our evolution has been so intertwined with heat from sun.
Yeah. There's that classic story in a whole bunch of cultures, histories about discovering fire, quote unquote.
Yeah.
Or that Greek mythology of stealing fire from the sun or something.
Right.
The guy whose wax wings melted. I don't know my Greek mythology.
I didn't know the Greek mythology, but I do understand. I remember
discovering fire. It's so fundamental. It's so primal. So you're right. I bet, I think I might have said civil engineering. Some experts say is the oldest one. But people...
It seems like thermal engineering.
Yeah, if they measured fire, I know people worshipped fire. People thought about it as a mystical thing. We light candles in church. But when did fire and heat and energy become a thing that people measure and harness and use and predict and use math on it?
I feel like... So when man invented fire, if he wanted a bigger fire, he needs to put 10 wooden logs in it. If he wants a small fire, he just needs to put 5 logs in it.
So people probably...
I think it's an intuitive understanding of these thermal, how heat behaves over time.
Or cooling. They were doing similar thinking.
Regions. So I think maybe we already have a very good grasp of how thermal system behaves.
Yeah, hot stuff goes to the cold. Yeah. People know that usually where does the heat go when you put the hot thing down?
Exactly. I guess this is thermodynamics is studying all of this in a much more molecular level, in a much more, we understand it a lot better, the three laws of thermodynamics, which we will talk about in terms of just conceptually in the future episodes. So, that'll be awesome to talk about all of those things.
Yeah. Oh man, there's so many topics
that
makes me
think I bet it's so intuitive. It's not like, hey, why are people spending so much money on...
Some of it's not as intuitive as I'd like, but especially when it goes to the biological side of things.
Yeah, you're right.
Oh my gosh.
Let's just bring down the whale.
The whale being thermodynamics in this
Yeah.
case. What else
Big
do we
words.
have to learn?
Okay, so
we talked about
covered
motion,
mechanics.
mechanics,
We talked
materials,
about materials. We spoke about
Thermodynamics.
But I think we should also break into mechanics, because mechanics is, you only mentioned it's also about, well, I guess maybe we covered it, everything.
You said forces and
Forces
stationary,
on-
static stuff.
Okay, statics. Yeah.
And there's like, if we made a Venn diagram of all this, there'd be intersections as well.
Oh, yeah.
We could talk about strength of materials, how beams break, for example, explosions and how things fail. I think
Right.
that's super interesting to watch. There's a bunch of YouTube channels where you can watch things breaking. There's a whole class or a whole field of studying that in mechanical engineering. You know, there is another thing that you made me think of when you said thermodynamics and we talked about energy. Another type of energy, I guess, is electrical energy. And I know we're doing mechanical engineering, but
No, it's a big field in mechanical engineering.
but today, especially today,
yeah.
there's circuits and electricity and all that stuff involved.
Basic electronics, at least.
Yeah, so I'm wondering, like, how far should we go in talking about circuits or mechatronics or robotics?
I think it is covered in a typical mechanical engineering curriculum in its basics. But I think when I look at it, you learn a lot about motors. And it's
You sound disappointed when you say
no,
that.
it's not a disappointing way, but it's essentially mechanical in nature.
So
An
electricity
electric
to
motor.
move things.
Electricity move things, but a motor is a mechanical device, right? It's electromechanical.
Yeah, no, that's a
device,
good point.
yeah. So I think even if electricity is electronics is electronics. What is electricity? What is the word for that?
Electronics.
Electrical, electronics.
Mechatronics.
Mechatronics. Okay, mechanical.
We'll have a whole
electronics.
episode about it.
Okay, yes. Mechatronics is definitely a big part of mechanical engineering.
You taught a little bit of that class, I think.
I have. I taught it for one semester at UT. It's fun because it kind of strays a little bit away from your typical mechanical engineering hands-on material, tangible things. A little more into this is a little bit magical,
A little more abstract, more magic. Yeah,
more magic.
It's the Harry Potter of our mechanical engineering.
A little
fields.
more into the molecular phenomena.
Magnets and things that we can't
Fields,
see.
yeah, it's more like just conceptual.
I can't see the electrons, so
Yeah.
they don't exist. So, okay,
No,
I guess
they do
we'll have an
exist.
episode about that.
Yes, that's
I have
definitely
a
a big.
lot to say about that, by the way.
Okay, that's awesome. You built a bunch of robots that I know.
Okay. Oh, well, yeah, so I had mentioned I was supposed to have studied robotics in grad school, and I did to some degree, but I didn't really continue it as much. And I feel like robotics is another one of those things that's a mix of mechanical and electrical
Right.
engineering, and it's related to mechatronics. So maybe we can touch on that there. But it's all about 3D motion these days,
Right.
and putting a bunch of motors together in a predictable way and programming it and energy usage, and it's very interesting. But we'll save that
Awesome.
for later. Hey, I'm also thinking about design. Speaking of robots.
Ooh, that's a huge
Yeah, we didn't
topic,
even talk about that. I'm surprised we didn't say that
How
first.
did we not miss that? Okay, wow.
What's
okay.
design, Southern? What is design?
Oh my god. Okay. I'm going to just tell a story. Okay, I'm not going to talk about what design is. I'm just going to tell a story.
Yeah.
So I did my undergrad in India. You know that.
We had a whole podcast talking a little bit about
yes,
it.
India versus US. Folks should listen to that. It's a completely different ways of approaching things. But I remember in my final senior year in India, we were, I guess it's everywhere in the world, as engineers, you're supposed to do a project. So the project is we were designing something. Okay, just let's leave it at that. We were designing something.
It sounds really suspicious now, but
Oh, no. Okay, so let me then put it out.
just make up something. We were designing
No,
another car.
this is not making up anything. Essentially, what me and my team were designing was we were making a robotic hand that can write
Oh,
letters, and the script specifically we were trying to make it write Tamil scriptures. And Tamil is it's a language spoken in southern India. It's one of the oldest languages spoken, and the scripture has a lot of curves in them.
yeah.
It's curvy, and it's actually very interesting why they are the way they are. But it's curvy in nature, and in order to get it to right was a problem, and we were trying to solve that problem. But the experience of tackling that problem in India was so hard because there was not a very good structure in place. In terms of how to approach the problem.
Nobody taught you
yes
how to design something.
They taught us how to design components, but
pieces.
How to approach a design problem was not taught. Yeah, there's two approaches to. Okay, what I'm talking about is the design methodology here. Mm-hmm. How do you approach a design problem? And it felt like we were left in the middle of the ocean. With no direction, and we had to plunge in, and we didn't know if the design we did was the optimal or the terrible. I had no idea. I was just like, oh, this solves the problem, and that's it.
So you actually did it though?
More of intuition than anything else. And then after that, I came to UT, and I was so surprised to find that there's an actual field called design methodology. Not design, that's a different thing that we'll talk about. But design methodology, there's a specific approach on how to approach a certain problem and come up with the most justified and optimal solution. Mm-hmm. And I ended up making it my research. I did my thesis on that. I teach as teaching assistant. I teach or support teaching that specific course at UT, the senior design project. So design brings a lot of memories from me. But there's one part of design you can talk about.
No, I don't have much to say. Like, that's a good story. I think that you remind me, as everyone should know, the University of Texas at Austin, I mean, I think their design program in the mechanical engineering department is really great.
Yes.
In that respect.
Yeah.
Because like you, I mean, we had a capstone project where we were supposed to design something back in undergrad in our last year before graduating, and they kind of just throw you in there. Now, I agree that like I didn't know what the optimal design methodologies were. I didn't know what these tried and true and studied strategies are to come up with a good solution in the fastest, most efficient way. And I might complain about that experience, but looking back, I actually like that I had the chance to design without any guidance first, so that when I finally learned these methodologies later, I saw the difference in what I used to think.
Interesting.
And I saw, these other methods that other people have developed, and I was like, oh, I see the need for these methods. Because I wonder if I had been taught some of those methods back then as a senior or something in undergrad, if I would have even appreciated or understood why I'm learning these things. Okay. So I think what I really take away from that is I would hope that anyone who is trying to learn engineering and how to design a solution, that they tried designing something just on their own without any guidance, kind of unstructured, kind of like we had, but do it at a younger age.
I never thought about it that way. I think that's
just have a reference point.
Yeah. I think that was the only reason I was able to appreciate it as much as I did.
But in any case, I totally agree. So that's all I had to add.
Awesome. So the other part of design, this was like more of design methodology. Mm-hmm. So there are certain mathematics principles that are already established.
I see.
When let's say you're trying to design a gear.
Yeah.
Okay, a gear is like a wheel-like structure with the teeth on the outside, and there's like a number of teeth in there. So how do you know what number of teeth to put in so that they're not slipping away?
Yeah,
so
there's
all of
formulas about how many teeth go around this size radius or whatever. Yeah.
So it's already been figured out.
Is that machine elements?
Yes. Yeah.
So I never actually. So there's a class in the University of Texas undergrad called Machine Elements that mechanical engineering majors have to take. I never took a class like that. I also was a bioengineer in undergrad.
That makes sense. Yeah.
But it would have been a class that I would have wanted to have taken looking back, because I ended up doing that in my workplace later. I had to build mechanical test structures, and it would have been great if I learned so much stuff that mechanical engineers are supposed to learn. But
No, that makes sense. I mean, I totally see why this is so irrelevant. Okay, so when you look at the mechanical elements, you're looking at gears, right? Gears, where is it used? In the car transmissions, you use gears.
Yeah.
Or in big machineries, you use gears. Looking at belt systems, where in big machineries, you're using belt systems. You look at cams. It's used in engines.
Anything to transfer motion and forces around to different places. Okay.
And also, like, I think it's a very valid name. It's called machine elements because they're not exactly, they're not a system by itself. They're part of a bigger machine. So these are small elements. And these elements is not something you design from scratch. There are already established mathematics that's involved in there. That will only we call it design, but essentially what you're doing is you're figuring out the best gear to use. You're figuring out the best shape of the cam to use.
Yeah.
So it is design in one way because there's so many possibilities.
Right.
That makes sense in the context of mechanical engineering because this is essentially working with a lot of machines.
Yeah.
But it does make sense in terms of biological systems. They're kind of irrelevant.
It depends on what you're doing. Bioengineering would be a whole really long set of episodes that would irritate me.
But I'm just curious.
Talk about
what
that,
do you just quickly, what do you learn instead of that?
Instead of, there's way more time spent on biological things. Like we had to take way more chemistry, genetics, biochemistry, stuff like that. And then genetics, by the way, one of my favorite classes. It's the most mathematical of all the biology classes.
Interesting.
Other than bioinformatics, which is more programming and stuff like that. But then we also had to take, bioengineering. You could choose different specialties within bioengineering. It's like majoring in a major.
Oh, same thing with mechanical engineering.
Yeah, exactly. And one of the concentrations, we'll call it, was biomechanics. And so I could have done that. Another one was biomaterials. Those are the two ones that I think were the most related to mechanical engineering. Biomechanics was about, forces, statics, dynamics, but like in organic systems. And biomaterials might be about designing artificial hearts or something. Like instead of designing aerospace materials made out of plastic and metal mixed together and ceramics, instead you're designing tissues made out of cells mixed in with polymers, mixed in with circuits, that kind of thing.
Interesting. Okay.
So, but you still had to worry about the same mechanical properties and all that stuff.
Right. But more on the mechanics side rather than elements, mission elements.
Yeah, but
makes sense. Yeah.
But the weird issue is depending on what job or research field you're going to do in bioengineering, you may have to learn a whole ton about gears. There's like, for example,
interesting. Okay.
There's there's a field called microelectronic machines or MEMS, and a lot of bioengineers use them because there are sensors in your body, like an ingestible camera pill, for example. Maybe there's a mechanical system in there that like swivels a camera around inside the pill so that when you swallow it, the camera is looking all around. And so there you would have to know about gears, but on a small scale or something. So like, it totally is. In my view, bioengineering is it's too broader. It's so hard to study because like you might have to be a perfect mechanical engineer.
It's like if looking at a Venn diagrams, it's an intersection of biology and mechanical
and electrical and chemical.
Biology. I get it.
It's all of that. But in any case, we'll save that for another discussion.
Yeah. So what else do you think is in mechanical engineering? So we looked at mechanics, I know this is like a long
dynamics. This is why it takes forever to get an engineering degree. This is why it's great that you're listening to this podcast instead. So now if you listen to us, they know, people who listen know a little bit about dynamics or motion,
mechanics,
statics, mechanics. They know about thermodynamics and heat and energy. They know that electronics is kind of involved, or mechatronics.
Yeah, design is a big field.
Design methodologies. And
I got one. Yeah. Manufacturing and production. This is definitely something that we learn as mechanical engineers.
Hey, so can I ask you a question before you get too detailed? Yeah. Like, I think that before I even studied this, I think there's a common maybe misconception where people think design and manufacturing are maybe the same thing. Like, so help me state what the difference is between design versus manufacturing.
Okay, so design ends with you having a final sketch and a final drawing
Like a plan,
like
is
a plan.
what you're saying.
Yeah,
Okay.
build. That's it. Once you have that, manufacturing starts. So in terms of where the design ends is you have the dimensions. Let's say you're designing a chair. Okay, let's say you're designing a chair. Simple. So all you're doing is you are thinking in terms of the dimensions. You're thinking in terms of the material. You're thinking in terms of how much force is going to be on going to be placed on that.
Like how heavy am I? And
where do you need to put some reinforcements? So you think about those things, and then you have a design, and then there's so many softwares, which is again something I wanted to talk to you. It's another part of it. Skills in terms of mechanical engineering. So you use all these softwares to at the end show that this is the shape, this is the material that I want this part to be, and that's the end of design. That's where you draw the line. So everything that happens in order to make that into a live, a chair, is manufacturing.
So then the person who's actually cutting the wood and putting in the screws or like
that process would be manufacturing.
Okay.
So once it goes in the physical side, actually building those things becomes manufacturing. So when you're designing the chair, you are thinking about, hey, how is this going to be manufactured?
Like I don't want to carve this chair out of a solid piece of wood, right?
Say it again.
Like I would not want to carve this chair that I've designed out of a solid block.
You can design, but the manufacturer is going to hate you.
Yeah,
it's just going to be harder to think.
Yes, manufacturers and engineering techs will hate the engineer if the engineer is a really poor designer.
Knowing how it's manufactured.
Yes.
So you need to learn to, I guess, as an engineer, you also need to learn, hey, what's the extent of our manufacturing capabilities?
Yeah.
And also assembly capabilities. So all of these things are taken into account when you design.
I think every engineer has to build the stuff that they create for the first couple of years so that they know how horrible they design things if they can't build it.
Yeah. If you are, I guess it goes in the realm of tinkering. You tinker with stuff and you see that, hey, this is an easy way to build. But essentially, you're learning all the trial and errors that past people have done, and they have a specific sets of rules and that you can learn, and then you can apply. So I guess that's the difference.
Yeah. So there would probably be a whole class on
manufacturing. Yes.
Manufacturing engineering, different ways to build things, and then how to design things so that you can even build them.
Yes.
In the first place.
Yeah.
Okay. And let's talk about software real quick because you mentioned skills.
I want to quickly mention a little bit about manufacturing as well. Oh. What is dealt in manufacturing? It ranges in a big way. I think most of manufacturing, they start as electives.
Right.
So in terms of manufacturing, essentially we learn at the very basic foundry. How to cast a piece of...
wow.
Yeah, it starts from
there. I never did that.
I did it. It was awesome.
You made your own metal... Did you make your own like molds and everything? And
we didn't actually go through the melting process or anything, but we just learned to do how to make a cast, the sand, and then the process continues, but we stopped it there. But UT does it.
That's cool.
All the way through. They use aluminum. I saw a few students working on it the other day.
Cool.
So it's pretty cool. It starts from there. It's just like foundry. Think about that. If you think about it, that's like 400, 500 years back they were doing that.
That's making swords and stuff.
Yeah.
Or plowshares.
That's probably a lot older than that because I know in India people are using swords like in 5,000, 6,000 years back. So yeah. So you start from there. You learn from those basics. And through electives, you can choose to learn the most modern. We were talking about 3D printing or nano manufacturing.
Yeah. Are there any other modern manufacturing methods? I'm trying to think.
I guess 3D printing is the
one that's always in the news and it's trying to go in every school.
That's where we hit a plateau right now. Yeah. So these are just going on. Anyway, so that's that's what I wanted to add in terms of manufacturing and production. There are also like small things that you learn here and there in terms of quality control.
It goes to industrial engineering a bit.
Kinda.
Yeah. But no, quality, you're right. There's more statistics and stuff involved in that.
That's not as necessary in the realm of mechanical engineering at the core of it. But maybe if we have time, we can talk about it a little bit.
Okay.
So skills.
Yeah, what do you mean by skills as opposed to these other classes?
Yeah, so I think the way I want to differentiate that is, so what we spoke about in terms of mechanics, in terms of thermodynamics, these are concepts that students need to learn, over time. But in terms of certain skill sets that they can develop, one of the main skill set is using computer softwares that will aid them in sketching things faster in a much more efficient way. So I guess we used to do, when we're talking about design, hey, how do you sketch these things? How do you, if you're designing a chair, do you use your hands and draw on a piece of paper? That's what they used to do. Now they don't do it anymore because it's just time consuming, easy to error to happen.
Right, not in any official records. It's not going to be some sketch on a napkin. Maybe when you're creating ideas, but
yeah. But if you're handing, once you're done with your design, if you're handing it over to manufacturing, there are certain rules you need to follow when you give them right. It's not So it used to be done with hand. It was called drafting. And then right now it's done in softwares like SolidWorks and CAD, and there are also softwares that will let you analyze those things in terms of if you want to on the software you can heat up the chair and then see how much temperature it'll take for it to
melt,
catch fire.
So you're simulating the thermodynamics.
Yeah, thermodynamics.
Or you're simulating maybe the forces when you smack it with a hammer or something.
Yeah. So all of those things can be done using softwares that's built by some companies. These are some of the things that students do learn during engineering. Not essentially as a part of a curriculum, even though it might be introduced as part of a curriculum. But most often than not, they learn by themselves outside of the classroom by doing it.
All right. Maybe in the company that they end up working for, they might train them how to use these tools. It's a tool, ultimately. It's like how to use a hammer.
Exactly.
It's an important tool. I mean, I've seen
it's vitally
sketching
important.
For mechanical engineers.
It's very, 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 very important.
Yeah.
And there are also software tools that can let you design pipeline systems, fluid mechanics, how much pressure should be there, where should you put a valve. So there's a lot of softwares that you learn outside of this core content.
Right.
So we will get to that.
There's one final thing. I think we covered a lot of the core stuff.
We did, yeah.
There's one final category of topics that I want to briefly talk about.
Okay.
So whenever you go to school to try to get an engineering degree, especially in undergrad, there's a bunch of stuff you have to learn that's not in the mechanical engineering, major. You got to learn some chemistry. If I look at the University of Texas's list of graduation requirements, you have to learn not only math, but you have to take a social science class. You might have to take a humanities class. There might be an engineering finance class. There might be a computer programming class or an art class or something. That's a lot of classes.
Yeah.
And so how much should we even talk about these other things that are not really traditionally part of mechanical engineering, whether it's engineering ethics or finance or art or any of that stuff?
Art? I don't think we should, because my understanding is this. I didn't. So there was one requirement for UT, was they had to take some kind of a governance class.
Okay.
Which was not a requirement for me when I was doing my undergrad in India. So they don't overlap at all.
Yeah.
So we can leave out the humanities and the arts part.
Okay.
We can talk about what they learn and why it might be important. For example, governance is important if you're in Texas, so you know where the oil fields are, what are the laws governing them. So for that it might be useful, but it's not a universal thing that you need to learn.
Right. I guess it's really specific to
regional
your
history,
job,
historical.
Lots of things.
Yeah.
Maybe what I can see is if we ever talk about any specific examples that are relevant to a particular field, like thermodynamics, we might talk about, the explosion of the shuttle Columbia or something. Then that might go into things like engineering ethics or government.
Yeah, that's true.
So I don't think it sounds like we're not going to have any specific episode on those things.
Probably not.
But I bet engineering, finance, and ethics and all that
those
stuff.
Those are different.
It'll come up.
Yeah.
Okay. Yeah.
The chemistry and the physics and
Sure,
the mathematics.
Yeah.
So one thing we are consciously avoiding is talking about mathematics to explain engineering concepts. We're not going to do that unless they're like some good
on an
concepts.
intuitive level.
Intuitive level, yes.
Like when things get bigger, something else gets small. The idea of more and less and like stuff like that. I think we can talk about.
Yeah. I'm saying like let's not. We're going to avoid talking about engineering with mathematical terminologies. We're not going to do that. So even though we're not going to do that, but
I think
as
that's
engineers,
great for what we're doing.
Yeah.
Like we're already talking for a long time without any math.
Yeah.
If we started bringing in math, it would be like that much more.
And also, it's like math is a huge ocean by itself. It's not something. We're not going to do that. That's just. It takes a different level of commitment to grasp those concepts before we can move on to.
You can talk about engineering without talking about the detailed math.
Yeah, we can.
So
totally.
That's what we're
going to try to attempt that, right?
We're gonna
as much as we can.
We can.
Yeah.
People do it. So we're gonna talk about all of that, Sadhan.
Yep, I think we'll get it going.
Thanks, Sadhan.
Thanks, Pius.
Till we meet again. This has been Sadhan Sathyaseelan and Pius Wong, your engineers for today. If you like this episode, stay tuned for more episodes where we go a little bit more in depth on mechanical engineering. For transcripts, links, and other notes related to today's episode, visit the podcast website, k12engineering.net. There you can also get links to our Facebook page, the Twitter profile, and more. Remember to subscribe to the show on iTunes, SoundCloud, or wherever you find your podcasts. And finally, thank you so much for the donors on Patreon who are supporting this show and all my projects in my independent studio, Pios Labs. If you like this podcast or any of the other projects that I'm doing, please donate too at patreon.com/Pios Labs. The opening music in today's episode is called Soar, and our closing music is called Polar. Both are by the artist Chris Pop. You can find more music by Chris Pop on SoundCloud under the username ChrisPop99. That's Chris with a CH, or just check the show notes for a link to his music. Thanks to Chris Pop for letting us use his music with permission. The K-12 Engineering Education Podcast is a production of Pios Labs. Thanks so much for listening, and tune in next time.